Hello everyone, welcome to this session on algorithmic problem solving. In this session, we would like to look at the problem of switching a sequence of railroad cars using a stack. Let's look at the definition of the problem and the solution.
Railroad tracks often are designed in a way that facilitates moving from one track to another or switching the linear order of the coaches. We can simulate the process of switching coaches using a stack. In the figure, the railcars arrive in a particular order from the right. The cars leave from the left. Cars can be withheld in the stack below before being sent on their way leftward. This facility can be used to permute the sequence of cars. The input to the railroad track problem is a pair of sequences describing the order in which the railroad cars arrive and the order in which we want them to leave. The goal of the algorithm is to determine whether such a transformation is feasible. Consider an example wherein we wish to detect if the sequence 1, 2, 3, 4 can be transformed to 2, 4, 3, 1. The first element of the sequence is 1. We push 1 onto the stack S. The next element of the sequence is 2. We push 2 onto the stack S. Next, we pop 2 from the stack S. 2 goes to the output. The next element of the sequence is 3. We push 3 onto the stack S. The next element of the sequence is 4. We push 4 onto the stack S. Next, we pop 4 from the stack S. 4 goes to the output. Next, we pop 3 from the stack S. 3 goes to the output. Next, we pop 1 from the stack S. 1 goes to the output. We have transformed the sequence 1, 2, 3, 4 to the sequence 2, 4, 3, 1. We consider another example. We are given the arrival sequence of cars as 1, 2, 3, 4, 5, 6. We need to determine if the sequence can be transformed into the sequence 3, 2, 5, 6, 4, 1. The configuration of the stack as the input is processed is shown here. We first push 1, 2, 3 in that order. Then we pop 3 followed by 2. Next, we push 4 and 5 followed by a pop of 5. Next, we push 6. Finally, we pop 6, 4, 1. The elements popped generates the sequence 3, 2, 5, 6, 4, 1. We consider another example. We are given the arrival sequence of railroad cars as 1, 2, 3, 4, 5, 6. We need to determine if the arrival sequence can be transformed into the departure sequence 1, 5, 4, 6, 2, 3. The configuration of the stack as the input is processed is shown here. We first push 1 and then pop the same. Next, we push 2, 3, 4, 5 in that order. Next, we pop 5 and then 4. Then we push 6 and pop 6. At this point, the sequence 1, 2, 3, 4, 5, 6 has been processed and the output 1, 5, 4, 6 has been generated. The stack contains 2 and 3 with 3 being the top of stack element. We can generate the subsequence 3, 2 from the stack. The required output is 2, 3 which is impossible to achieve. We conclude that in this case the sequence 1, 5, 4, 6, 2, 3 is inadmissible. Let us now present the algorithm pseudocode in Python code snippet for solving the railroad car problem. Assume that the input sequence is given as AList and we need to transform this to BList. If the top of stack element matches the next element from the target sequence BList, we pop from the stack. Else we push the next element from the input sequence AList onto the stack. Now let us analyze the complexity of the algorithm. We assume we are given an input sequence and a target sequence, each of length n. In each iteration either an element is pushed onto the stack or an element is popped from the stack. We also note that across the entire duration of the algorithm, each element gets pushed onto the stack exactly once. Each element gets popped off the stack at most once. Moreover, each element gets popped out of the stack at most once. In case of an admissible permutation, all elements get popped off the stack. In case of an inadmissible permutation, some elements may remain on the stack. Hence overall, the time taken is order n. Thank you. This course is brought to you by Elahay Technologies.